Assalamualaikum warahmatullahi wabarakatuh and a very good day. I'm Ahmad Fitriadhy, School of Ocean Engineering, University Malaysia Terengganu. Hello everyone, welcome to our MSc program for the subject Naval Architecture and Shipbuilding, which is composed of two videos, part 1 and part 2. Having discussed the portion of the center of gravity and buoyancy in the previous section, currently we are discussing on their relative position affect the transverse stability of a ship. As the learning objective, on completion of this topic, the student should be able to explain comprehensively several basic terms on transverse stability of a ship, discuss stable, neutral, and unstable transverse stability of a ship based on the value of metacentric height, describe the effect of ship geometry and weight of cargoes on board on transverse stability of a ship, and calculate moment of statical stability of a ship for small and large angle of heel. As a preamble to the aforementioned learning objective, the fundamental question appear in our mind is, what is the transverse ship stability all about? Before I proceed to answer that question, let us see the animation here, which can assist us to have the correct answer accordingly. Referring to that animation, as seen in the stage, the ship is initially in the upright position, then sea heel to other side. Due to presence of a restoring moment, finally the ship return to the upright position. Then I can conclude here that the transverse ship stability is a term used to describe the ability of a ship to return to the upright position as she has been forcibly held by an external force. When the external force is removed, inherently the existing moment will return the ship to the initial upright position. Referring to this answer, keep in our mind that the transverse ship stability data is basically reflecting the ship worthiness in seaway during the sailing. To know this in detail, usually we can find those data in the ship stability booklet. Dear all students, referring to the figure 1 that was snapped from the animation 1, it is necessary to describe earlier here, although this point will be discussed in the next slide. Basically, the transverse ship stability is divided into two categories. First is the initial stability, where the ship is held to a small angle of inclination up to about 5 degrees. And second category is the large angle stability, where the ship is held to large angle of inclination, which is greater than 5 degrees. To get more clear understanding of this ship stability, it will be discussed on the next slide. Before we further discuss on the transverse ship stability, general understanding of its basic term, as noted in the first objective, should be clearly defined. To achieve this, let we see in the figure 2. Referring to that figure, there are term of G stand for center of gravity. I can explain here that the center of gravity is the point at which all forces of the gravity acting vertically downward direction on the ship. Meanwhile, B stands for the center of buoyancy, is the underwater geometric center of the ship. It is the point at which all forces of buoyancy acting vertically upward direction. As referred to the gravity and the buoyancy point, we can say here that in case of the gravity and buoyancy forces act on the same vertical line downward and upward respectively, the ship is known as floating in the upright position. Dear all students, the next term we should know is the metacenter and written as M as shown in figure 3. With respect to that figure, which is snapped from the animation 1, definition of the metacenter is the point that was formed at the intersection of the vertical line through B in the initial and subsequently healed position. Further detail of the metacenter term will be explained in the second objective of this course later on. As well referred to the figure 4, several extension terms on the transverse stability of a ship are also defined accordingly. The first term is kg, which is defined as the center of gravity and measured from the reference point K, or keel. The next one is kb, which can be explained as the center of buoyancy and measured from the reference point K. Furthermore, if we define a distance between B and M point and written shortly as BM, we can call it as the metacentric radius. Similarly, we measured the initial static stability of a ship and calculated as the distance between G and M and written shortly GM, we name it as the metacentric height. Noted here that this particular term will be appropriately discussed in the second learning objective. Referring to the similar figures, the next term is km and define a distance between K and M measured from the reference point K. Dear all students, in this slide, to know the meaning of the lightning lever term, let me explain to you with respect to the animation 2. As seen in the presence of external force, a ship is then held to a side. This causes her equilibrium condition inherently also changed. Referring to the animation, the center of gravity point, or G, of the ship does not change to somewhere else, meaning to say that the force of gravity acts vertically downward through its initial point as well as in the upright position. Referring to the figure 5, which is snapped from the animation 2, however, the buoyancy point being the center of underwater section of the ship has now moved laterally to a new center of buoyancy point that acts vertically through B1. It can be concluded visually from the figure that the forces of gravity and buoyancy are no longer on the same vertical line. In fact, this will create a lever or arm of moment. Dear all students, what I want to highlight, the important point here is the perpendicular distance from G to the vertical line of B1. This lever is known as lightning lever, or GZ. To obtain more understanding for the lightning lever GZ characteristic in various angles of healing, we can find it in the animation 3. When we snap the figures from the animation 3, figure 6 shows that the lightning lever GZ changes when the vessel is subsequently healed. In addition, the most substantial point from the figure 6 is to evaluate some GZ values with respect to the healing angle of a ship, as will be shown in the next slide. In this current slide, we see visually from the animation 4 that lightning lever are plotted against the angle of heel, and this resulting graph is then called as GZ curve, or lightning lever curve. Dear all students, the GZ curve is actually a representation of a ship stability characteristic. What we can observe from the respective animation here, the GZ value is proportional with the sum angle of heel, and adversely it decreases as the ship consecutively heals further. In this slide, through the GZ curve, several information related to the ship stability performance can be obtained as follows. One of them is the range of positive stability as shown in figure 7. It was given from 0 degree up to about 80 degrees. Other information we can obtain from the GZ curve is the maximum value of the lightning lever Z, which is typically occurs between 30 degrees to 45 degrees as displayed in the figure 8. The next one is to obtain the approximate maximum metastatic height or GM as shown in the figure. Dear all students, from the current slide, we can also know the point of vanishing stability beyond which the ship will capsize as clearly presented in figure 10. And other important information from the GZ curve as shown in figure 11 is we can evaluate the dynamical stability of a ship which is obtained as the product of the area under curve multiplied by the ship displacement. Dear all students, the next related term on the transverse stability of a ship is the moment of statical stability. Let us see the animation 5 here. It is shown that when the ship is heeled, buoyancy point shifts up from the center line, while gravity point remains in the same location. Referring to the movement of the buoyancy point as shown in the previous slide, it results the forces of gravity and buoyancy acting in the opposite direction. Inherently, a moment is then developed as shown in the animation 6 here. In this situation, the existing moment of statical stability is actually required to restore the ship to the upright position as displayed in figure 12. As you may know that this moment is called as moment of statical stability. Dear all students, referring to the figure 13, the moment of statical stability is commonly calculated as the product of the ship displacement acting vertically downward through G multiplied by the righting lever or GZ, as written in equation 1. Again, I want to stress the point here that the moment of statical stability depends on the righting lever and also the ship displacement. Hence, we can conclude here that merely the magnitude of the moment statical stability for any angle of heels represent as the instantaneous response of the ship to return to the upright position. Dear all students, as noted in the earlier slide at the beginning of the lecturing, as well as the ship stability is divided into two categories, therefore, the moment of statical stability is also expressed into ship stability condition. First, stability at small angle, and second, stability at large angle of heel. Referring to the figure 14, in case of the ship stability at small angle of heel, here given 0 degree to 5 degrees, the formula of theta in the triangle GZM is derived and expressed in equation 2. Therefore, the moment of statical stability for small angle of heel is the product of the righting lever multiplied by the ship displacement as expressed in equation 4. It should be noted here that the equation of the righting lever ZZ in case of small angle of heel is obtained as GM's time to sinus theta as well written in equation 2. In case of the ship stability at large angle of heel, meaning that greater than 5 degrees, the formula righting lever ZZ can be obtained using the wall-sided formula. Through the comprehensive derivation of equation, the final formula of GZ is expressed in equation 5. Hence, formula of the righting moment at the large angle of heel can be written as expressed in equation 6. Dear all students, I do hope that this lecturing provides a lot insight into understanding several basic terms on the transverse ship stability. And before we complete the first part of this topic, let me summarize several conclusions as referred to my explanation regarding to the first learning objective. First, what is the definition of the transverse stability? Second, several basic terms on transverse stability such as gravity, buoyancy, metacenter, kg, kb, km, zz, and moment of statical stability. Third, category of the transverse stability based on the magnitude angle of heel. And fourth, derivation of equation of both small and large angle stability. Thank you for watching, and see you again in part 2 as the extension topic discussing about the learning objective 2, 3, and 4. Thank you.